All right, thanks everyone. It's such a pleasure to be back in Cambridge. I did my PhD here with Andy, wherever he ended up. And in 2015, I left here in 2015, and it's just wonderful to be back here to tell you a little bit about the work that I've been doing with some of my own students at MIT. Okay, so what I wanted to tell you about today, we just heard this talk from Andy on persistently accreting AGN, standard accretion in AGN. And what I want to tell you about today is some new surprises in black hole accretion related to tidal disruption events and a new phenomenon that we call quasi-periodic eruptions that may be the electromagnetic counterparts to LISA-detectable EMRIs. Okay, so I think it's fair to say that the field of tidal disruption events really got started here at the IOA, and we've heard a lot about Martin Rees's impact on the field. He theorized that these tidal disruption events, when a star gets too close to a supermassive black hole and the tidal forces from the black hole shred the star apart, and that star can accrete onto the black hole very quickly. He theorized that this could happen. And it could take a quiescent black hole, a black hole that's not accreting a lot of material, and suddenly it can become as bright as an AGN. And indeed, we do see tidal disruption events now. I think we have about 150 in the literature now. And some of them emit in the X-ray band. So this is just kind of showing you a comparison between tidal disruption events and typical standard accretion AGN, just so you can kind of set the stage for the differences that we see. So in AGN, Andy told you that the emission in X-rays is, you see ubiquitous in all accreting black holes, all accreting AGN, is that you see this hard X-ray emission coming from this corona, this hot corona, this billion-degree plasma close to the black hole. But in tidal disruption events, when you get this newly formed accretion disk around the black hole, you do not see a corona, and instead you see only thermal disk emission. No corona in these tidal disruption events. Also, so I'm plotting on the right here the corresponding light curves for these 3 different AGN. They're all 10 to the 6 solar mass black holes, and you can see that the one telltale sign of an AGN is that it shows X-ray emission, and that X-ray emission is stochastically variable. But what you can see with this tidal disruption event, gosh, I'm going to switch to the other one here. With this tidal disruption event for the same mass black hole, you don't see very much variability. Pretty smooth variability. And I think tidal disruption events are a really nice opportunity. We still don't know how this corona is heated, right? And the tidal disruption events are a nice opportunity to study, both the, turbulence in the accretion disk itself, and perhaps what are the conditions that you need to create a corona. Okay, so that's kind of setting the stage, the differences observationally in the X-ray band between standard AGN and tidal disruption events. So now I want to tell you about a very special tidal disruption event called GSN 069. And this is a paper from Giovanni Minuti. So this is the kind of, what we typically expect now from a tidal disruption event. It was a previously quiescent black hole, and it became very bright and decayed with this power law over time. Shows thermal emission like standard tidal disruption events do. And in 2019, Giovanni Minuti came to a conference and presented to all of us like a result that just my jaw dropped. And everyone in the audience was talking about it for the rest of the conference. And I really hope that at some point in all of your careers that you have the opportunity to go to a conference where you see also a paradigm shifting result happen. So no pressure to any of the future speakers at this meeting. Okay, so what Giovanni showed us was that when they followed this source up, after the flare, they got this long XMM observation, and it showed what we kind of now have come to expect from TDEs, that they don't show very much variability. And then, following up a couple of years later, they found not stochastic variability, but instead very periodic flares. And this is what we call these quasi-periodic eruptions. So like, who ordered that when we're used to seeing stochastic variability, and now we're seeing these really quasi-periodic flares in the nuclei of low-mass galaxies? And now there's currently 8 QPEs known, and there's a ... there to suggest that there's more in the pipeline coming. And again, they all show the same thing, that they're very soft thermal emission, and the flares show this kind of hard, just like still very soft, but a little bit, hotter, hotter temperature black body required there. So I got interested in the field of QPEs because I was at this conference like everyone else, and I wanted to know, like, okay, so we just found that, that QPE kind of serendipitously. Giovanni looked at the light curve and it kind of smacked him in the face. And so what we were wondering is, have we missed any of these in the archive? And I wanted to, this is a paper with my graduate student, Johin Chakraborty. It's from a couple years ago now, but I wanted to bring it here because we are this broad audience. I know there's exoplanet folks in the room, so I wanted to tell you that we used an algorithm that the exoplanet community has used to find exoplanet transits. And what is an exoplanet transit but a QPE turned upside down? And so we applied this CATS algorithm to the entire XMM archive and found one more candidate, just one. So this is only showing 2 flares here, but it has very similar characteristics to all of the other QPE sources in that it has no corona. Again, a very unusual thing for a supermassive black hole to only show thermal emission, no hard X-rays. And again, the flaring is very similar to other QPEs. And again, what was most exciting about this result was that this became then the second QPE coincident with a tidal disruption event. And so it became clear that this was a previously known tidal disruption event candidate. And when we look back in these archival observations, we found this QPE structure. So QPEs, these quasi-periodic eruptions, are associated with some, if not all, tidal disruption events. So the question is, like, what are they? And I would say at this point, we have 8 QPE sources and many, many more theory papers that have come out to explain them. So we're still kind of in that regime. But overall, these QPE models kind of break down into 2 broad categories. One is disk instability models, and I saw Chris Nixon here. You can talk to him about models where you have, perhaps disk tearing, and you can see, quasi-periodic eruptions on the same kind of timescales that we observe in these sources. And the other kind of broad class of models are these extreme mass ratio in spiral-based models, where you have a supermassive black hole at the center, and you have a star with an accretion disk around it, and a star that is, or a star or a compact object or a black hole that is punching into the disk, twice every orbit. And those flares are from the impact of that star with the accretion disk. And I think that the jury is still out as to which of these models will win out. But what I'll say is that, what I like about the Emory-based model is that you can make really clear predictions, right? You should be able to predict if this is something related to the orbit, right, that you can time these things and predict over time, including perhaps things like, apsidal precession, nodal precession. But this is kind of where we're at now, is like trying to test these Emory models in light of many years now of TDE observations, QPE observations. So so this is just highlighting Johin's recent paper, but please also take a look to Ricardo's paper. He's an Einstein Fellow at MIT that just came out last week. So in the last half of my talk or whatever, I want to tell you about another object that has, I think it's now become my favorite AGN. And this is 1ES 1927. It's the gift that keeps on giving. So this is a source, discovered with the Einstein satellite. So it's been an X-ray source that we've known about for a while now. But in 2018, ASSASSIN, the optical time domain survey, discovered that there was a flare. And it decayed over time as t to the minus 5/3, which is typical for the mass fallback rate of a tidal disruption event. And so it looks like a TDE that's happening in a known AGN system. And what was really special about this observation, this source is only at like 80 megaparsecs, but what was particularly exciting about this nearby TDE candidate was that there was amazing X-ray observations pre-outburst, which is something that we don't usually have because we don't really have many, like large all-sky surveys that give you really high quality spectra. But XMM had taken an observation, pointed observation of this source, and this is what it looked like in 2011, pre-outburst. So again, it shows hard X-ray emission. It just looks like a typical AGN. It showed stochastic variability and a hard X-ray spectrum. And after the flare happened in the optical, we got another spectrum with XMM. And what we see is a total change, right? So the X-ray, the hard X-ray emission just disappeared by over 2 orders of magnitude. And what you're left with instead is this very characteristic thermal spectrum that is very characteristic of tidal disruption events. And so what we were seeing was the destruction of the corona, right? So we got these observations. We were monitoring with XMM Newton, that's the star there, but also with NICER, and you can see that those are not error bars, that's actual fluctuations in the luminosity. And the source, started very bright, and then over 50 days, it kind of turned off, which is sort of what we would expect from a tidal disruption event. And we were, we said it was a good go. It was really fun to watch that happen, but we were starting to not observe it anymore, not detect it anymore. And we almost stopped taking observations, but then we realized that actually the show is still going on. And so the source actually became the brightest X-ray source, extragalactic X-ray source in the sky for about a year, over a year. And now we have continued to follow this up with our collaborators, and Megan Masterson is leading this work now. So you can see this is the first observation I told you. It shut off, it came back up, and it has just for a year hit the Eddington limit for a 10 to the 6 solar mass black hole, which this is based off of the M sigma mass. And then we've been following this now for several years. It kind of decayed back down to its normal pre-outburst level. And the spectrum went back to being a very hard X-ray spectrum. I forgot to mention that the corona kind of turned back on, where we're watching this corona build in real time for the first time. And the corona turned back on. It looked really just like it did in its pre-outburst state. And we were kind of honestly I was getting a little bit bored with this object because, how long can you keep measuring, taking measurements here? But then recently, just in the past couple of months, we've recognized that there's actually the most exciting part about this source is the discovery of Millihertz QPOs. And so this is, instead of that flat line that that's become typical of tidal disruption events, and it's not like stochastic variability like we see in other AGN systems. Here we're seeing quasi-periodic oscillations at millihertz frequencies. And QPOs are kind of like a tough field to get into, and especially in extragalactic sources. Are you seeing them? Are you not? How many cycles? These are highly significant. Each one of these has at least 50 cycles, so it's clearly like a 4 sigma in each one of those individually. And we've been observing these millihertz QPOs in this source for about a year and a half. And still today, still showing QPOs. So now we have these QPEs, these flares that we see every couple of hours, 8 hours, to sometimes once a day. And we have also in 1ES 1927, a QPO, 10-minute oscillations. And what's interesting about these objects is that they're very similar in their other, in other properties. They show this thermal soft X-ray spectrum. They're in these 10 to the 5, 10 to the 6 solar mass black holes. They exist in post-starburst galaxies, and now, as of this morning, we all know what a post-starburst galaxy is. They don't show broad line regions. They're transient events. I think that they're very similar sources. Even though we're seeing these oscillations now on much faster timescales, I think there's good evidence to show that these two are actually one in the same source class. So if, we still don't know, is this due to disk instabilities or due to some kind of emery-based model? But if it is an emery, and the QPEs, the quasi-periodic eruptions that we see on hours timescales, if those are due to orbits at like 100 RG, maybe mildly elliptical orbits at 100 RG, what this is suggesting is that this is like a later stage of the evolution, and you're seeing something at like 10 RG or less, some circularized orbit much, much closer to the black hole, which would be very exciting. So those with a keen eye may recognize that that QPO at 10 minutes it wasn't constant. It was actually evolving in time. So this is the first time that we've been able, this is the third QPO ever detected in an AGN in a supermassive black hole system. And the first time that we're able to measure a P dot. And not only that, we're actually able to start measuring like a P double dot. And what we were excited about was that, if this is due to gravitational wave radiation, we have very clear, if we're talking about an orbiter that's like at 10 RG or even smaller scales, we should make predictions for like when we should not see that QPE, that flare anymore, because that compact object should eventually accrete onto the black hole. And we made predictions, but you can see it's actually the evolution, it's decelerating over time. So these are the predictions that you'd expect from gravitational waves given this 10 to the 6 solar mass black hole for a range of companion masses. And you can see it's clearly not that. It's not gravitational wave driven if it is an orbiter at all. And so what we've been thinking about are there other models that we can, that could, be allowable in this emery-based model? And if you have like a white dwarf companion and a supermassive black hole, as the central object, perhaps you can take from the white dwarf, ultra compact binary literature where you can actually get stable mass transfer that would like allow for this to slow down and kind of park and maybe even turn around, move out to out spiral. So I would say like we have work to do in terms of we're making clear predictions for what is to come next. With the evolution of these QPOs. But what is clear is that, if this is an orbiter, and because this source is only at 80 megaparsecs, what we can say is that this is in the millihertz regime. It's in the LISA detectable band. And because it's so close, it would actually even be observable with LISA at an SNR of 7. So just to kind of put this in context for LISA, here are the known QPEs on our timescales, and this source 1ES1927 is now squarely in the millihertz regime. And what we need is an X-ray telescope of the future to match the depths of LISA, and that is AXIS, an X-ray probe that we're putting into the NASA probe competition. And I will leave it at that and take any questions. Thanks.